Hey everyone, ready for a deep dive? Today we're going to tackle something that, well, it sounds kind of simple at first, but it gets, surprisingly tricky. We're talking about figuring out all the different ways you can arrange zeros and ones
Right.
without having too many ones in a row. Sounds kind of abstract, right?
You might be thinking, hold on, why should I even care about arranging zeros and ones? But here's the thing. These binary strings, they're actually super important. They're like the fundamental building blocks of how computers, store and process all that information we rely on.
Yeah, it's like imagine a light switch. It can be on, which we'll call a 1, or off, which we'll call a 0. Now picture a whole bunch of these light switches all lined up. That's basically a binary string, and they're like everywhere in the digital world.
Exactly. And you know what's surprisingly important? Figuring out how many valid combinations of those zeros and ones we can make, especially when we have certain rules, like limiting how many ones can be right next to each other. This comes up a lot in things like coding theory, data compression, all sorts of areas.
Yeah, and this actually came from a listener who is like wrestling with this exact problem. They're trying to figure out, how many possible binary strings you can create of a certain length, but without having too many of those ones all bunched up together. It's kind of like, remember those combination locks we had as kids?
Oh, yeah.
Instead of numbers, we're dealing with zeros and ones.
That's a really good analogy. So let's say you have one of those simple locks, like with 4 digits, but you can only have at most 2 ones right next to each other.
Huh.
How many different combinations could you make on that lock?
Our listener, they figured out 13 possible combinations.
Okay.
Which sounds about right?
Yeah.
But here's the thing. When you start making that string of zeros and ones longer, figuring this out, it gets really, really hard really fast.
Yeah.
Like imagine trying every single combination on a lock with like 1,000,000 digits.
Oh, yeah.
It would take forever.
It would take forever, even for a computer. Just trying every single combination, it's just not going to cut it. It's not practical. Especially as that string grows, the number of possible combinations, it just explodes. Even computers would be like, whoa, slow down. We need a smarter approach here.
Okay, so we need like a shortcut or something.
Yeah.
Something more clever.
And that's where this idea of dynamic programming comes in. It's a problem-solving method, and it basically helps us tackle these big, complex challenges by breaking them down into smaller, more manageable pieces, bite-sized pieces. Dynamic programming, it's all about working smarter, not harder.
I like that.
Yeah. It's like, think about building a house. You wouldn't try to build the entire house all at once, would you? You'd go brick by brick, right?
Yeah.
And each brick you lay, it makes it easier to lay the next one.
Okay, I like where you're going with this. So how does this whole brick by brick idea, how does that apply to our, binary string problem?
So instead of trying to calculate every single possible combination all at once, right?
Mm-hmm.
What we can do is break this big problem down into these smaller, more manageable subproblems.
Yeah.
And each subproblem, it focuses on just a smaller segment of that binary string. And we figure out how many valid combinations there are just for that small segment.
Okay, so we're basically chopping up this long, scary string of zeros and ones into these smaller, less scary chunks. But how do we keep track of all these little sub-problems and their answers? This feels like we need a whiteboard or something.
It's like we need some way to organize all of this, right? This is where this idea of a DP table comes in.
A DP table.
Yeah, imagine it's like a table.
Okay.
It helps us organize all of our work.
Okay.
And each cell in that table, it represents a specific subproblem and its solution. So it's like a little storage unit for each part of the problem.
Interesting. So we got our sub-problems, we've got this DP table to keep everything organized.
Yeah.
Now, I got to ask, how do we actually fill in this table? Where do we even begin?
So imagine the DP table, right? Like a grid, almost like a spreadsheet.
Okay.
And the rows in our table, they represent how long the binary string is that we're thinking about.
Okay.
And we start with a string of length 0. That's going to be at the very top of our table.
Got it. So if we were trying to figure out the combinations for a binary string of length 4, in that lock example, we'd have 5 rows in our table.
Exactly.
1 for 0, 1 for 1, all the way up to 4.
Exactly. Now the columns, those represent how many ones we have in a row at the very end of the string. So we might have a column for 0 ones in a row, 2 ones in a row, and so on, depending on what the rules of our problem are.
So if we're allowed to have a maximum of 2 ones in a row, like with our lock example,
yeah,
we'd have 3 columns, 0 ones, 1 1, 2 1.
Exactly. You got it. And each cell in our table, it represents a specific subproblem. It's like, okay, of this, the string is this long and it ends in this many ones. And the number that we put in that cell, that's how many valid binary strings fit that exact description.
Okay, this is starting to make sense. But how do we actually figure out what number goes in each cell?
Yeah.
Like, where do we start?
Well, we start at the very beginning, right?
Okay.
The first cell in our table, the one that represents a string of length 0 and no ones at the end, how many ways are there to have a binary string of length 0 with no ones at the end?
Well, there's only one way. It's nothing.
Right.
So, yeah. So that would be our starting point then.
Exactly. From there, we use basically a set of rules to kind of like fill out the rest of the table, and we're always building on the calculations that we've already done.
Right.
So let's say we're looking at a particular cell in our table, right?
Yeah.
To figure out its value, we've got to think about two things, like what happens if we add a 0 to the end of our string?
Okay.
And what happens if we add a 1?
Okay, so we're like strategically building these binary strings one digit at a time.
Yeah.
And then seeing like how many valid combinations we can make.
Yeah, exactly. And adding a 0, that's the easy one.
Okay.
Because adding a 0 always resets our count of how many ones we have in a row back down to 0.
Yeah, because you're breaking that chain of ones.
Yeah.
Okay. So how does that work in our table then?
Let's say we're looking at the cell that represents strings of length 3 ending in a 1.
Okay.
To figure out how many valid combinations there are, what we do is we look at the cell above it.
Okay.
That represents strings of length 2 ending in a 0.
Okay.
Because basically by adding a 0, we reset that count.
Okay.
We're carrying over that information.
Okay, so adding a 0 means we look straight up in the table to that 0 column. Easy peasy.
Yeah.
Okay, what about adding a 1? It seems a little trickier.
Yeah, adding a 1 is a little trickier because it can either like extend a streak of ones that's already there,
Right.
or it can create like a brand new streak.
So how do we account for both of those? It seems like we need to look at like multiple cells in the row above it.
Exactly, yeah. So
Right.
when we add a 1, we actually look at 2 cells from the row above.
Okay.
The first one, it's the one directly above, which represents having one fewer 1 at the end.
Okay. I think I'm with you. So we're like thinking about what happens if adding that 1 makes our streak of ones longer.
Exactly.
Okay. What about that second cell?
The second cell, that's the one that represents ending in 0 ones,
Yeah.
again in the row above it.
Okay.
Because, our new 1, it could be starting a totally fresh streak. It doesn't have to be continuing an old one.
Right.
Yeah.
Okay, so we're taking those two numbers from those two cells and we add them together.
Exactly.
One for continuing the streak, one for starting a new one.
I see. That's
Yeah.
pretty smart. And that's how we find the value for our current cell.
Wow.
We're basically saying, all right, let's look back at what we know about shorter strings, both the ones that end in 0 and the ones that end in 1,
Right.
and use that to figure out how many valid combinations we have now.
Okay, so we just keep doing this, like going through our table cell by cell,
Yeah.
using these rules and using the work that we did before until we have this whole DP table filled out.
Exactly.
Okay, now for the big question. How do we get to our final answer? Because it seems like we just have this like grid full of numbers staring back at us.
Yeah. So the answer is actually way simpler than you might think.
Yeah.
All we got to do is add up all the values in that very last row of our DP table. Because each cell in that last row, remember, that represents how many valid binary strings there are of that target length that we wanted.
Right.
With a specific number of ones at the end.
So when we add up that whole last row, we're basically saying, we don't care how many ones are at the end. We just want to know how many total combinations there are.
Exactly. We've gone through everything, every possible scenario. We've accounted for all of it.
Yeah.
And we have our final answer.
And we didn't have to do it that brute force way of like trying every single combination.
Exactly. No brute force here. This is the beauty of dynamic programming, working smarter, not harder.
I love it. It's like we've got this secret code to solve these problems. But okay, let's go back to the beginning, to our original example. String length of 4, max of 2 ones in a row. If we build out our DP table, do we get that magic number 13?
We absolutely do. That last row, it's going to have 3 values in it. One for strings ending in 0 ones, one for 1 1, one for 2 ones.
Okay.
We add those up and boom, 13.
Amazing. It's like our DP table just knows the answer. But, I always like to think about the bigger picture. Like, where does this kind of problem solving, where does this actually come in handy in the real world?
Oh man, dynamic programming It's everywhere. Like encoding theory, which is all about making sure that communication is reliable.
Okay.
So think like you're sending a text message, right?
Yeah.
Or data from a spacecraft, or even just streaming a movie.
Okay.
Dynamic programming helps design these codes that